Let's suppose that we want to make a solution out of acetic acid, CH3COOH, and its salt, sodium acetate. If you want to start with 0.10 molar, for example, of each solution, the normal question for these guys is, what's the pH of the resulting solution? The first step is to really think about what chemicals you're pouring into a beaker. We're going to have our acetic acid in here, and he's mostly going to be in his together form, but because of his Ka value, every once in a while that guy will split into H+ and A-. Then you're also going to have this completely soluble salt break up into its two pieces, sodium ions and acetate ions. Now we have to think to ourselves, which parts of these chemicals are the important parts. Now we know the acetic acid is going to act like an acid, and we know that the acetate ion is going to act like a base because it is the conjugate base of the acetic acid. We can ignore the sodiums for now because they're going to behave like spectator ions. Now to figure out if our solution is going to behave like an acidic solution, where the acid will split into hydrogen ions and the anion, or if our solution is going to be controlled by the base, we have to compare the K values of these processes. If you check your textbook, there's usually tables of K values. For acetic acid, the Ka value is 1.8 times 10 to the negative 5. And the Kb value for the acetate ion is 5.6 times 10 to the negative 10. Now, if we look at these values, all we have to do is figure out which number is bigger, and that is the one that's going to control the reaction. We see now that this Ka value is much bigger than the Kb value, so our solution is going to behave according to acid patterns. Now that we know that our mixture of chemicals is going to behave like an acid, I'm going to write out the full equation. CH3COOH, when dissolved in water, dissociates into CH3COO- and the hydronium ion, which, don't forget, behaves just like H+ in all of our calculations. Okay, then I can set up an ice table. Don't forget to ignore water. It is a liquid in this case, so we don't write it in our equilibrium expressions. And I could take my arbitrary numbers of starting 0.10 molarity and 0 for the hydronium so far, and 0.10 molarity for the acetate ions. Now, some of you may be wondering why I may choose to put a 0 here when we know that there might be a little bit of that acetate, or rather the acetic acid, splitting originally before you add the salt to it. And that's all fine and good. You could do 2 ice tables if you wanted to, but it's kind of a waste of time. Because of Le Chatelier's principle, when you add in that acetate ion into solution, it's going to shift it left anyway, so you might as well just do 1 ice table taking care of both situations at the same time. Okay, so let's start this fresh. We know that since we have a 0 over here, that we can assume that our reaction is going to shift to fill that 0. And we'll end up with 0.10 minus x and 0.10 plus x and x in our E portion of our ice table. Now, it's really important to remember for most of the online homework questions that these x values are so small that we can assume that they're not important. for the subtraction purposes. Basically, that means that they're so small that when you do sig-fig rules for subtracting, it wouldn't change our number. Now, we could go the old route and solve the problems the way we did in the last chapter, where we could have our Ka value equals the products over reactants. And then we can plug in our numbers. We have 1.8 times 10 to the negative 5 equal to 0.10 times x divided by 0.10. And then we see that we have a little bit of canceling going on here. If you have your weak acid and your salt starting at the same concentration, this pattern always holds, where our hydrogen ion concentration is going to be equal to our Ka value. And that can be a really important pattern to recognize on exams. So now we see that our hydrogen ion concentration is 1.8 times 10 to the negative 5. And we can go ahead and plug that into our pH formula. So pH is going to be the negative log of this number. And we'll see that we have a final answer of pH equals 4.74. Now the new way, after learning about the Henderson-Hasselbalch trick, is that we could use that new equation, pH equals pKa plus the log of the anion concentration over the acid concentration. And we could see that the same situation happens. We have the same number in that log, 0.1 over 0.1, which means that we would be taking the log of 1. And since we know our log rules, we know that that guy is 0. So we'd end up with the same situation. pH is equal to the negative log of the Ka value, which is 1.8 times 10 to the negative 5, which would give us a pH equal to 4.74. So either way you attack the problem, you'll end up with the same answer for pH.